and logs. Okay, so that's going to be kind of cool. So here's dv. dv is all the other stuff. So u takes care of that, and then dv is going to be the dx alone. So got it. We take the differential, we differentiate the u and get du. 1 over 1 plus x squared. That's your dx piece. And then dv, we try and get v out of it by integrating. We go backward, and that means just x. These are the components for our subs. This is what we use for integration by parts. There's a u, there's a v, there's a du, and there's a dv. Okay, we use all that stuff. Here's the formula again, in case you forgot it. uv integral of, sorry, I wrote that wrong. The integral of u dv is equivalent to uv minus the integral of v du. And all those things are up above. So here's our u, here's our dv that we're integrating. And now we're going to set it equal to u dot v. So that's this is where the Zorro kicked in. Yesterday I didn't mention it, but are you going to feel it? Can you go with this? You like go pew, pew, pew. See that? Want to see it again? I can undo that. Pew, pew, pew. Whoops. Whoops. Pew, pew, pew. So it's like Zorro. Mildly dyslexic Zorro, but Zorro. Right, same kind of thing. Okay, we'll keep going. uv, which would be x arctangent of x. Are you okay with that? u dot v. And minus the integral of v du, which would be the integral of x times 1 over 1 plus x squared. So I'm just going to put them together to see what we get. Bibbidi bobbidi boo. Salagazoo meets Menchikaboo. Part of it's done. Anything that's out of an integral is done. What we look at now is, can I integrate what's left? And that is doable. That's where all that u substitution practice you all got into comes in handy. Because now we can say, all right, done with this, x arctangent of x, gotcha. And the integral of this would be a nice u sub where u is your denominator, 1 plus x squared. The derivative, that's 2x. Because I'm missing 2, I got a 1/2. So you're really integrating 1 over u, so it's just 1/2 natural log of whatever u is. Dun, dun, dun. Done. This is lovely. I want to show you the whole thing. Can you see the whole thing now? Look at that. That is integration by parts. Pick your u by Lipit. Get your u, dv, du, and v. Derive and integrate. Sub it into the formula. Integrate the integral that's left. Probably u substitution-ish. Maybe something else. Are you feeling okay? Can I roll? Okay. Keep rolling. You can say no. X arctangent of x. Well, that throws a wrinkle in things. What's Lipit say about that? So if I go Lipit into shape, go for it. Get it straight. Just Lipit. You want to see that, right? Have you heard that song, Lipit? Listen. I'll play it for you. Play it loud. Here. Just listen, they say, you just lip it. And then it's all about integration, especially you know the song, Lip It. Lip It. I used to think it was Whip It with the W, but that was when I had a wisp. But now that I don't have a wisp anymore, I know it's Lip It. So I want you guys to see this on the screen. Let's go full size here. I gotta have this. Yeah, it's got that Lisp thing in there. Don't mind that. That's when I wrote that earlier. Here. It really is lip it, but that's like my 3-year-old saying it, whip it. That's what he would say, because Ethan has a wisp. So lip it, he says whip it. But look at those right there. You see those revolution of solids? We're going to do that. These are a bunch of math nerds made a band about lip it. And it just went nuts in the 80s. It's a great song, great album. Okay, so should we get back to the math, or is probably not? This is way too fun. Okay, back to work. So here we are with the song in the background. Crack. Uh-huh. We'll turn it down a little. You just lip it. You just lip it. Yep, you hear that? Inverse polynomial. That means inverse function, inverse trig, totally wins getting picked for you. Move ahead. Just lip it. Oh, wait, no. You lip it good, and it just annihilates that integral. I mean, it eats it up. There it is. You good with my stuff? du. Hey, derivative arctangent. We did this like the other day. 1 plus x squared. Keep that one in the back pocket. You cool with that one? Derivative arctangent. Okay. V 1/2 x squared, because we integrate on that side. And then we just start the uv. So our original is equivalent to u and v. So let's do u dot v 1/2 x squared arctangent of x minus the integral of v to u. Crack that lip. That happens this time of year. It's so dry. You guys notice that? Okay, done. Right? We can integrate that last one, I think. I mean, what? So uv minus the integral of v du. What on earth am I going to do with this? How do I integrate this one? U substitution, right? The derivative of x squared. Oh no. It worked when I had I had x on top, because the derivative of 1 plus x squared helped me replace that. I need another method, and we've done this before. Do you remember what it is? The degree on top is as the same or greater than the degree at the bottom, the denominator. You long divide. Nice job. You came through. Yeah, this part needs long division. So wherever you have long division space on your paper, you got to go after it. So here goes. X squared plus 1. We are going to divide you into x squared plus 0x plus 0, otherwise known as x squared. And it goes in, x goes into x squared is 1 time. Multiply it out, you get x squared plus 1. Change the signs and add down. So you go make this negative and add them down. And I get 0, 0, and -1. So this little dude is the same as -1/2. Remember, it's the quotient. So plus the remainder over the divisor. So it's 1 plus -1 over x squared plus 1. Oopsie. My screen twisted. And then that little piece is -1/2 x, because the integral of the one piece is x. Oh, we know the integral of this one right here. Uh-huh. Are you seeing it? The enemy of tangent. The arc enemy of tangent. So I believe if I distribute that -1/2, we're going to get a positive arc tangent over 2. Got to see that arc tangent coming, and then plus c. Now we can bring down the rest of it that was from earlier. Here is our complete antiderivative. So I brought this down. Isn't that something? Love this part stuff. Just lips it right. Just lip it. Okay. So now, what about theta arc secant? Have you had your fill of arcsecant lately? Okay, back by Austin's popular request. He asked for this the other day. Can we integrate arcsecant a little more? Inverse trig function over a polynomial. If you can't see how this works and you have trouble with the thetas, theta is just another variable. It's like an x, so you can call it x if you want to. So you're more than welcome to change it over. But it might be good exercise to remind yourself to use theta. So I'm going to try really hard to write theta, and I guarantee I'm going to write an x somewhere in here. Just hang in there. So you pick u as your arc function, like inverse secant, arcsecant, another way to call it. And then dv is the theta d theta. We derive on the left, du, and we've got this run, right? 1 over, let's see, there's that x again, darn it. I already did it. 1 over the absolute value of theta. I mean, it's this one. Now you have to remember the theta squared minus 1. Arc sine has the 1 minus theta squared. Oh boy, this is. But that's the derivative. V is 1/2 theta squared. Easy. Thanks, Phil. Okay. Feeling pretty good? Let's do this thing. So UV, it's a little Zora action. Okay, so we're going to go 1/2 theta squared arcsecant theta. Got it. Minus the integral of v du. Ooh, this is going to be, I'm going to put the 1/2 out front. Theta squared over theta. Now, oh my Lanta. Oh my Lanta. What now? Do you have any thoughts on this one? How are you going to tackle that one? U substitution is not looking good again. And then I got that extra theta out there. Oh, that's a tricker. What do you want to do? Maybe theta and theta squared? Yes. Cancel them. Yes. Yes. You got it. Okay, so we got minus. Let's just fixate on that part because that's the part we need to work on. This ends up being just, oopsie, almost wrote an x. You saw it. Theta squared minus 1 d theta. So this opens the door then to u substitution. It's not the easiest use. I mean, we got to do a little work, but if we just focus on that part of the integral and then stick it in with the rest that's already finished to the left there, we're done. But we have to integrate that. So you go off into your happy place. Take that integral with you to make it even happier. You start picking out things like, hey, u, why don't you be theta squared minus 1? And then, 1/2 du is your theta d theta. And you use that to substitute into that equation there. So your brand new integral is 1/2. And with u substitution, I get another 1/2 inside there. So it ends up being 1/2 times 1/2. And then I'm going to do u to the negative 1/2. Okay. So with that u substitution, it's going to be like integrating u to the negative 1/2, and then we'll put u back when we're done. So it'll be 1/4, and we add 1 to that power to make it positive 1/2, and divide by half, which is actually times 2. U to the 1/2, and I'll put u back, which is theta squared plus c. That's just that circled part. So we just took care of that one piece. And I should probably put the minus, the minus is part of it, so maybe we should put that in there too. Kind of left it out, but it's got a minus going for it. I think we're ready to throw this thing back together again. The final deal, let's put it right next to the original, should be 1/2 theta squared secant, arcsecant. And then our new, and now that negative 1/4 and 2 is negative 1/2. I'll highlight this here. And then I like square root if I can use it because it looks cool. theta squared minus 1 plus c.